Next, let's explore the sequence r to the nth power and figure out for what values of r the sequence is convergent. Let's start with something we're all very familiar with, and that's a number line. And I'm going to label 0 here. Let me scooch it over for more space. I'm going to label -1 here and 1 here. And all I have is a real number line. And r can live in any of these places. So for case 1, I'm going to suppose r is greater than 1. So let's look at the case where r is larger than 1. So r could be a number like 2 or 3 or 4. So since r is larger than 1, and I'm taking powers of r, so for the n equals 1 case, we'll have r. For n equals 2, we'll have r squared. For n equals 3, we'll have r cubed, and so on. And I want to see, is this sequence increasing or decreasing? What happens if we multiply both sides of this inequality by r? That is, we multiply by r on both sides. We'll end up with r squared is greater than r. So if say r is here, that means r squared is bigger. What if we repeat this process? We'll end up with r cubed is greater than r squared. R to the 4th is greater than r cubed. And if you notice, every subsequent term, here's r squared is larger than r, so r squared will be here, r cubed will be here, r to the 4th. And for every subsequent term, our sequence gets larger and larger and larger. What does that actually tell us? This tells us that as n approaches infinity, r to the nth power approaches infinity. So if r is larger than 1, then the sequence r to the nth power is divergent. Next, let's look at our second case. So let's say r lies between 0 and 1. If r lies between 0 and 1, then r is a fraction. R not only is a fraction, r is a fraction that's actually greater than 1. So say, let r equal a over b for positive integers, a and b. And since I stated that these integers are positive, then this clearly excludes 0, so I don't have to worry about saying b not equal to 0. They're both positive, so b is just not equal to 0. Well, let's see what happens in this case. And I'm going to mark my number line again, and I'm just going to say, suppose a over b lives right there. That's where it is on the number line. Well, what happens in that case if I multiply this inequality by itself? That is, if I have 0 less than a over b less than 1, and I multiply each part of this inequality by a over b. Well, what's going to happen? I'll end up with 0 is less than a squared over b squared is less than a over b. So a over b is here on my number line, and a squared over b squared, that is r squared, is somewhere over here. Let's keep going. What if I do this again? Then I'll end up with 0 is less than a cubed over b cubed is less than a squared over b squared. So I have a over b, that is r living here, and suddenly r squared is here, r cubed is here, and if you notice, we're tending to get closer and closer and closer to 0. So the more times we multiply r by itself, we'll tend to 0. That tells me that r to the nth power is convergent on this interval from 0 to 1. Before we look at negative cases, let's consider both the values of 0 and 1. And I'll do these here in green. But before I do that, I'm going to quickly make some more space. And let's just call both of these case 3. So first, if r equals 0, then r to the nth power equals 0 to the nth power. And as n approaches infinity, 0 to the nth power approaches 0. If r equals 1, then r to the n equals 1 to the nth power. And as n approaches infinity, 1 is to the nth will approach 1. If r equals 0, if r equals 0, As n approaches infinity, r to the n approaches 0. If r equals 1, as n approaches infinity, r to the n approaches 1. So in this case, either way, we know for case 3 that this sequence is convergent. Next, let's consider the case where r lies between -1 and 0 in this region. So we could, again, name a fraction and multiply it to itself and show that it goes closer to 0. But instead, we already know. Now, notice if this inequality here does hold, then 0 is less than the absolute value of r is less than 1. So as n approaches infinity, the absolute value of r to the n also approaches 0. So in this case, we again have a convergent sequence that is approaching 0. Now let's look at r is equal to -1. Let's call this case 5. So r is equal to -1. Then our sequence is actually -1 to the nth power. And what happens in that case? This is actually the same sequence we saw in our warm-up video, so you can find it in Canvas or the first video of this playlist. And what does this look like? Well, this is just going to go back and forth. So here's 1, 2, 3, 4, and this is n. And our sequence, if n equals 1, is at -1 here. When n equals 2 is at 1, when n equals 3 is at -1, when n equals 4 is at +1. So our sequence jumps back and forth between 1 and -1 without ever tending to any value. So the sequence is divergent here. Finally, let's look at the last part of the number line that we haven't talked about at all. That is, let's explore the case when r is less than -1. So this is very similar to case 1. And if you remember, if r is greater than 1, then as n approaches infinity, r to the n approaches infinity. Now in this case, r is less than -1, but the absolute value of r is greater than 1. So very similarly, as n approaches infinity in this case, the absolute value of r to the n will also approach infinity. So we again have a divergent sequence if r is less than -1. And now I'm going to add one more thing to this. If you're having trouble seeing this, let's just take any value for r that's negative. Say r equals -6. Or let's try something smaller. R equals -2. And notice I've marked my vertical axes from -40 to 40, and these are n's. So when n equals 1, r is just going to be -2. So r will be really close here. When n equals 2, r is going to be 4. When n equals 3, r is going to be -8. So we're getting closer to that -10 value. When r equals 4, we get +16. So suddenly we're all the way up around here somewhere. When n equals 5, we're over at -32. And when n equals 6, we're at +64, which is just off of my chart. So as you can see, for every subsequent value, we're going higher and higher and higher. So, in conclusion, the sequence r to the n converges as long as r is greater than -1 and at most equal to +1. Furthermore, the limit as n approaches infinity of r to the n varies. Our limit equals 0 in a few cases, this one, and this one. So clearly, the limit as n approaches infinity of r to the n equals 0 so long as r is greater than -1 and less than 1. If r equals 1, then the limit is just 1. And that's this case here.